right, Daltons and ideal. So here we go. The combined gas law with Boyle's, Charles, and Gay-Lussac's. Therefore, you only usually use two variables in those. But as we know from the balloon example, that when the balloon went up in the sky, did the temperature really stay constant? No. So there are plenty of times where the gases will have all three variables switching. This happens when we're dealing with this. We need to use the combined gas law. As you can see, they merge them all together. Also here to the right, this one merges it with Avogadro's as well. Most of the time the moles, though, are not changing, so you just take them out of the equation. But occasionally, like I said, they might ask you one where the moles do change, or they decide to add gas or take away gas, and therefore they're changing the particle number. But you can use this version of the combined gas law in those cases. So, basically here we're going to do a couple example problems. Gas occupies a volume of 20 liters at this pressure, so I'm just going to start labeling. This is volume 1, this is pressure 1, this is temperature 1. Okay, what will the volume be if the pressure is raised to 10 atm? Pressure 2. The temperature is changed to 250 K, that's T2. So which variable are we missing? Volume 2, that's the one we need to solve for. So once again, you write out your formula, P1V1T1 equals P2V2 T2, but you know, as I've said before, I don't like that way, so I do the P1V1T2, P2V2T1. Then you just plug them in and cancel and go for it there. So P1's 5 atm, V1 was 20 liters, T2, 250 K. Over here, P2 was 10 atm. V2 we are missing, and then T2, our T1 was 500 K. Now once again, look for canceling of units. So ATMs cancel with ATMs. The K's cancel with the K's, so we're left with liters. That's what we want, and we want a volume measurement anyways. Now multiply everything over here and divide it by the 10 and the 50, or the 500, divided by both of those values, and then you'll get your V2. Now, how many significant figures should we keep here? Look at our measured values in our problem. Yes, most of them have 1. There's only one up there that has 2, so we're going to keep 1. And go with 5 liters. Did you get 5 liters? Multiply the left side, divide by 10, and then divide by 500. See if you get 5 liters. Alrighty, second problem. And I think I changed this, so make sure that you put the extra dot in there for the 500 milliliters. I did change that because I wanted the significant figures to be different. So go ahead and make sure that you do that. Sample of nitrogen gas is stored in a 500 milliliter flask at 108 kPa and 10 degrees Celsius. So these are all my ones. This is volume 1, this is pressure 1, this is temperature 1, and what do I need to do to that? Add the 273. Good. So this is going to be 283 K. The gas is transferred into a 750 milliliter. This must be V2. Flask at 21 degrees Celsius, that must be T2. And then I need to add my 273, which is going to give us what? 294 K. Now we know all our values. Which one are we missing?
Pressure 2.
Pressure 2 is missing, so that's the one we have to solve for. So we have P1, V1, T2, P2, V2, T1. Let's plug them in. The first pressure is 108 kPa. The first volume is 500 milliliters. And the second temperature is 294 K. Over here, P2 is what we're missing, so we put that in there. The second volume is 750 milliliters, and our first temperature was 283 K. When you plug and chug and do all of that, how many significant figures should we keep? 3. What do you get for your value? Anyone? Anyone? Yes, no, yes, no. Anyone? Of course, it's in my here. So it is 74.8 kPa. Did you get that?
Yes.
Good. All right. Now, this last one here, very simply put, follows the same. We have a gas occupying a volume of 200 liters at a pressure of 2 atm and a temperature of 300 K. What will be the volume if the pressure is raised to 10 and the temperature is changed to 1000 K? Ooh, that's quite a high deal. So this is also solving for V2. That's what we're missing. So plug it in. P1, V1, T2, V2, V2, T1, 2 atm times 200 liters times 1000 Kelvin equals 10 atm times, we're missing, no, we got the pressure too, we're missing the volume too. That's what my variable is there, and my first temperature was 300 K. And you can watch the cancel K's go. ATM cancel, so of course we're going to be left with the liters there. And what do we get for our answer and how many sig figs? Yes. And we're going with 100 liters. I know it seems like a silly answer, but that would be the correct number of significant digits. All right, now off to the really, really hard gas law, Dalton's law of partial pressures. You're going to think it's really, really challenging. The pressure of a mixture of gases is equal to the sum of the pressure of all the gases in the mixture. So we have a container that has 3 different gases in there in this particular example. Gas 1 is exerting 200 kPa. Gas 2 is exerting 500 kPa. And gas 3 is 400 kPa. So they're all occupying the same container. You just added the pressures, and they simply add up to giving you the total pressure in the container. So this is simply put, it's an addition problem. P total equals P1 of the partial pressure of the first gas plus the partial pressure of the second gas plus the partial pressure of the third gas, and so forth. And if you had 4th gas in the mixture, you'd add the 4th gas in there, right? Okay, you kind of get the idea. So, once again, add the dot here because I wanted the sig figs to work out right, so I changed this, so make it 600 dot. We have a mixture of gases that has hydrogen and helium in it. Basically here, the total pressure is 600 millimeters of mercury, and the partial pressure of the helium is 439. So this is how you'd write it out. Total pressure is going to be the partial pressure of the helium plus the partial pressure of the hydrogen. And that's the notation they use for partial pressure. They put a P and then you do like a subscript for your gas. Okay? Now, the total, of course, is the 600 millimeters of mercury. It gave us the partial pressure of the helium, which is 439. So we simply have to find the partial pressure of the hydrogen. This is really complicated math, guys. Go for it. So, do your quick subtraction, right? What do we get? Subtract the 439 from the 600 to solve for the partial pressure of hydrogen. you get 161 millimeters of mercury. I told you this was the hardest gas law out there. Now let's look at a different scenario of the problem. In this particular case, they're giving air from a blast furnace contains a total pressure of 3.7 atm, and 85% of the air is oxygen. What is the partial pressure of oxygen near a blast furnace? Okay, yes, they also tell you that, 15% of it's nitrogen in your problem. I understand that. But do we even really need to know that if we're only looking for oxygen here? Gave us a percentage of our total. So what does a percentage actually tell us? A percent is going to be the part over the whole, right? Okay, times 100. That's the normal percentage equation, right? Part over whole times 100. So what do we have to do here in order to figure out our partial pressure of oxygen, which is the part? Partial pressure of the oxygen is going to be what? P total times the percent. And what do we do to our percent? Make it into a decimal. So yes, we would do 3.7 atm times 0.85. And what would be the partial pressure of the oxygen then? Did you get 3.1? Yes, as you can see, this is really, really difficult, hard math, right, guys? I know, you get the sarcasm in my voice. Okay. The last scenario of Dalton's that you'll see on the SOL looks like this. It's collecting gas over water, and this is done in the lab. Okay? In a water bottle or any container with a liquid, the liquid is in equilibrium. It is evaporating and condensing at equal rates. So there's this little layer that forms on top of the liquid called the vapor pressure. It's this tiny little bit of vapor pressure on top of the liquid. What does that mean to us? Well, if you look here, when you're collecting gas over water from a reaction, you have your reaction vessel over here, and the tube goes into the water, and the gas comes up here and it starts collecting in your either graduated cylinder or some kind of measuring device. The problem is, as the gas is collecting and pushing the water down during doing water displacement, there is a little bit of vapor pressure in there from the water. And so when you're collecting your certain product of gas, you don't want to know how much of it is from the water. You want to subtract the water out so you get the pressure only exerted by your gas. It's a very simple alteration to the Dalton's law of partial pressures. What you do is you have the P total is going to be your gas that you're collecting plus the partial pressure of the water that you're collecting it over. But the partial pressure of the water, the vapor pressure of the water, varies with temperature. So for one of these problems, they have to give you the chart with the temperatures and how much is vapor pressure at that temperature. Okay, so they'll give you the chart. Of course, you wouldn't have to memorize that. So let's look at an example problem. We're collecting the gas by water displacement at 40 degrees. The total pressure ended up being 110 kPa. Use the table to determine the partial pressure exerted by the gas. While we have, PT equals P gas plus P water. Now, 110 kPa. Here is our P gas. Now, at 40 degrees, what do we have here? Which one is our partial pressure? We need to look at the 40. So this is where we would go. So yes, it'd be 7.38 kPa. Subtract the two real quick, and you get your partial pressure of your gas. And it's 102.62. Both of those measurements go out to the hundredths, and since this is addition subtraction, we follow those significant figure rules. So in these problems, they have to tell you the vapor pressure of the water at the different temperatures in order for you to be able to calculate it. You would not be expected to memorize them. It would be in a table. Now for the best one, the ideal gas law. It's the most complicated and fun. So we call it PIV-NRT. PV equals nRT. Additional factors in here. We have the N, which is now the moles, and R, which is called the universal or ideal gas constant. Another set of numbers that you would not be expected to memorize. The universal gas constant is actually even on the AP formula sheet, so they give them those values and do not expect them to memorize them. So the difference is, though, if you're looking at, there are three different options for our R value. We have 0.0821, and that is liters times ATM over moles Kelvin. That's its derived unit. We have 8.314 liters per kPa over moles Kelvin. And last but not least, over here we have 62.4 liters times torr, or millimeters of mercury, it doesn't matter, over moles Kelvin. Out of all of those, what is the only unit that's varying between them? Each one of them has a moles per Kelvin. Each one of them has a liters. The pressures are different between each value, so that's what's going to dictate to you which R value you should use. So look at your pressure measurement in your problem to decide which R to choose to use. Okay, so if my pressure in the problem happens to be ATM, I'm going to use the 0.0821 number. If the pressure in my problem was millimeters of mercury, I'd use the 62.4. Just depends, you have to select it. Now, like I said, on the SOL, they will give you these R values. You do not have to memorize them. I will give them to you on the quiz or test as well. Once again, identifying our variable is not too hard. P means what? Pressure. V means volume. But the volume has to be in liters for this one. It has to. As you see, all your R values are in liters. N is moles. R is the ideal gas constant. What is T? Temperature in Kelvin. Thank you. Temperature in Kelvin. So let's work a few problems here. Let's take a look. Determine the temperature in K. 2.49 moles of gas contain 1 liter vessel at a pressure of 143. Since the pressure is kPa, which R value shall I select? The 8.314. Because that one is going to be the one that goes with kPa. And then you simply plug in and calculate. So, luckily, they were very kind to us and gave us and provided the R value for us in the problem. So, we are missing the temperature. So, pressure 143 kPa. The volume here is 1 liter. The moles, 2.49 moles. Now, I'm only going to do this once. I'm not going to rewrite it every time. 8.314, this is liters times kPa over moles Kelvin. I'm going to show you why I do this. And then we're missing T. We're missing the temperature. The reason why it has this funky unit here is because they have to cancel the other units. So liters cancels with liters. kPa is going to cancel with kPa, and the moles are going to cancel with the moles, so we're left with our temperature unit. So that is the whole purpose of making the R value have that very interesting derived unit. So it cancels all the rest of them in the equation. And if we calculate this, what does our temperature end up being? 6.9 K, and it is very cold. We're getting down towards absolute zero. One other thing, I want to do one more. I have like 2 or 3 minutes. I'm going to skip problem 2 and go on to problem 3 because it's a little bit different. Let's look at this one real quick. What is the pressure in atmosphere? So it wants ATM. But here it gives you grams. It doesn't give you moles. So what do you do with that? You must change it to moles first. So I have grams of helium. I need to change that to moles of helium before I can even begin. And it ends up being this value. I'll just do it for you real quick because we're running out of time. That ends up being the mole number for the helium. The only other thing here that I have to change, look what they gave me here. I have to add 273 to it and get 293K. Then I can set it up because everything else I have liters. They even gave me the correct R value to go with atmospheres. PV equals nRT. So we're looking for pressure. We have the volume. We know the moles now because I changed it from the grams. We have our R value. And we know our temperature. You set it up, now you can solve for the pressure. And this would be our answer. We would go with 3 significant figures because all the measured values have 3 significant figures. One other thing, you would never base your significant figures off of the R because it is a constant. It is not a measured value.